Roll 2 dice 1,000 times and something unfair happens. 7 shows up way more than anything else. Snake eyes, double sixes, almost never. And the first time I noticed this, I assumed the dice were rigged. They're not. Each die is perfectly fair, every face equally likely. But the sum is wildly unfair, and I want to show you exactly why. Because the reason is this one operation that also, and I'm not kidding, is the thing your phone does when it blurs a photo. Same math, completely different costume. So keep your eye on that number 7 for a second. It's not lucky. It's just standing in the widest doorway. There are 6 different ways to roll a 7. 1 plus 6, 2 plus 5, all the way down. There's only one way to roll a 2. That gap, 6 paths versus 1, is the whole story. But counting paths gets old fast, so let's find the machine that does the counting for us. Start smaller. One die. Forget the cube, I just want the numbers. Faces 1 through 6, each with probability 1 over 6. I'm going to draw that as 6 little stacks, all the same height sitting over the numbers 1 through 6. Boring, flat, perfectly fair, and it looks perfectly fair. This flat row of equal stacks, that's our whole object for now. Think of it as a strip of possibility, one slot per outcome, and the height of each slot is how likely that outcome is. When everything's equally likely, you get this dull flat line. And honestly, that's the point. Fairness looks flat. The interesting shape, the triangle from a second ago, has to come from somewhere. It's not in one die, so it has to be born the moment we combine 2 of them. And combining, it turns out, is not adding the pictures. It's something sneakier, and the sneaky part is what has a name. Here's the move. To get the odds of a sum, say the sum is 5, I need every pair of faces that adds to 5. 1 and 4, 2 and 3, 3 and 2, 4 and 1. Watch what that looks like. I take the second die's strip and I flip it around, then I slide it across the first one. At each position, wherever 2 slots line up, I multiply their heights and add up everything that overlaps. That total is the probability of that sum. Flip, slide, multiply the overlap, add, that's it. And when I do it for every sum from 2 to 12, the overlaps are tiny at the ends and fat in the middle, because in the middle the strips overlap the most. 6 slots line up right at 7, 1 slot at the very edges. The triangle isn't magic, it's just how much 2 flat strips overlap as one slides past the other. That operation, flip one, slide it across the other, multiply the overlap, sum it up, has a name, and the name is convolution. And I'll be honest, the name is intimidating, and the symbol is worse. It's a little asterisk, which is the same symbol programmers use for multiplication, which is a fantastic decision that has confused everyone for decades. I'm sorry on behalf of mathematics. But the idea underneath is exactly what you just watched. You're asking, for every possible way to hit a target total, how likely was that particular way, and then you add up all the ways. Convolution is a machine that takes 2 lists of weights and produces a new list that answers, if I combine one thing from each, what's the distribution of the result? 2 dice was just the friendliest possible example. The lists were short and flat, but nothing about the machine cares that they were dice. Let me prove the machine doesn't care. Add a 3rd die. Now I don't want to count triples in my head. That's a nightmare. 30-something combinations. Instead, I just feed the triangle back into the machine with one more flat die strip. Convolve the 2 dice triangle with another flat die. Flip, slide, multiply, add, same as before. And look what comes out. The triangle rounds off. The sharp point at the top softens into a gentle hump. The corners bulge outward. Do it a 4th time, a 5th time, and here's the thing that genuinely gave me chills the first time. It starts turning into a bell curve. That smooth bell you've seen 100 times, the normal distribution, is what you get when you keep convolving simple flat things with themselves. The bell isn't assumed, it's assembled, one slide at a time. Okay, dice, fun, but I promised you photo blur, so let me switch costumes. Forget probability for a second. A grayscale photo is just a grid of numbers. Each pixel is a brightness, 0 for black, high for white. That's the whole image, a big spreadsheet of brightnesses. Now, what does it mean to blur it? Intuitively, blur means each pixel gets smeared into its neighbors. A sharp, bright dot on a dark background should spread out into a soft glow. So think about one single pixel. To blur, I replace it with a mix of itself and the pixels around it. Take a little of the left neighbor, a little of the right, a little up, a little down, average them together, and that average becomes the new pixel. Do that for every pixel and the whole image goes soft. Now say that sentence again slowly. Take a weighted mix of a thing and its neighbors and add them up. Does that sound familiar? It's the dice machine again. The little set of weights, how much of the center, how much of each neighbor, that's a tiny grid of numbers called a kernel. And blurring an image is nothing but sliding that kernel across every pixel, multiplying the overlapping values and adding them up. Flip, slide, multiply, add, the exact same 4 steps. In dice, the 2 strips were both probability distributions. In blur, one strip is your image and the other is this little kernel of weights. But the operation, the actual arithmetic the computer runs is identical. It's convolution both times. When I first saw this, I actually laughed because I'd used both of these things for years and never once suspected they were the same animal. The dice were teaching me image processing and I had no idea. And once you see the kernel as just a little grid of weights, you get power because you get to choose the weights. Make the kernel a wide flat patch of equal values. That's a box blur. Every neighbor counts the same and it looks a little harsh. Make the kernel a bump, high in the middle, tapering off at the edges, and you get a Gaussian blur, the smooth, pretty one, where nearby pixels matter more than far ones. Notice that bump, high in the middle, low at the sides. That's the same bell curve the dice were building. The nicest blur in your photo editor is shaped like a pile of dice sums, and that is not a coincidence. It's the same object showing up because you're doing the same operation. The kernel is where all the personality lives. Change its shape, change what the machine does. Here's where it gets a little dangerous and a lot more fun. Who said the weights have to be positive? In dice, negative probability is nonsense. You can't roll a face negative 1/6 of the time. But an image kernel is just numbers. So let me build a mean little kernel, positive in the center, negative all around it. Now slide it across the photo on a flat region where every pixel is about the same brightness. The positives and negatives cancel and you get roughly 0, black. But right at an edge where brightness suddenly jumps, they don't cancel, and you get a big spike. Run this across a whole photo and the flat areas go black while the outlines light up. You just built an edge detector. Same convolution machine, I only changed the numbers in the little grid, and instead of blurring the image, it traces every boundary in it. Let me clear up the one part that trips everyone, including me, for way too long, the flip. Why do we flip one of the strips before sliding? For a symmetric kernel, a blur that's the same left and right, flipping does literally nothing, so people skip it and get away with it. But it's not decoration. The flip is what makes convolution line up cause and effect correctly. Think of it as each output slot asks which inputs could have landed here. And to answer that, you have to look backward, which is exactly what the flip does. If you skip the flip, you get a closely related operation called correlation. And for symmetric kernels, they're identical, which is why nobody notices. But the dice made us flip the second strip, remember? And it's the same reason there. Adding to a total means running the second die backward relative to the first. The flip was always there. Dice just hit it because a die strip flipped looks the same as before. And once the disguise drops, you start seeing this thing everywhere, which is honestly a little overwhelming. Sound. When you add reverb to a recording, a voice in an empty cathedral, you're convolving the dry sound with the echo pattern of the room. That echo pattern is the kernel. Moving averages and a stock chart, that's convolution with a flat strip. The same box blur just on a line of prices instead of pixels. the blur in a camera lens that's slightly out of focus. That's a physical convolution happening in glass and light before the sensor even sees it. And the neural networks that recognize faces, the C in CNN literally stands for convolutional. They learn thousands of little kernels and slide them across images to find edges, then shapes, then whole objects. It's the dice machine, scaled up until it can see. Every one of these is flip, slide, multiply, add. So let me put the whole thing in one picture, the one I'd want you to screenshot. On the left, two flat dice strips sliding into a bell. On the right, a photo and a little kernel sliding into a blur. In the middle, one word, convolution, and the four little steps, flip, slide, multiply, add. These are not analogies. They are not similar. They are the same computation run on different inputs. The dice hand you probabilities. The photo hands you brightnesses. And the machine does not know or care which one you fed it. When I finally saw these two things snap together, this whole messy pile of separate topics I'd learned, statistics, image editing, audio, machine learning, collapsed into basically one idea I could hold in my hand. That's the feeling I chase. One machine wearing a lot of costumes. Here's the thread that still bugs me, and I'll leave it with you. Every example I showed, dice, blur, reverb, all of it was flip, slide, multiply, add, done slot by slot, and for a big image that's a staggering amount of multiplying. But there's a trick, and it feels illegal. If you take both things over into a different world called the frequency domain, using something called the Fourier transform, convolution stops being this whole slide and sum ordeal and turns into plain ordinary multiplication. Just multiply point by point, done. Slide a kernel across 1,000,000 pixels the slow way, or hop into frequency space and multiply, and you get the exact same answer, dramatically faster. Which raises the question I don't fully have my head around yet. What is that other world, where the messy thing becomes the easy thing? That's the next one. Go roll some dice while you wait.